So the organizers asked me to talk about nuclear deformations. So I decided to do some brain dump here and to tell you about nuclear deformations, the origin, and what are the issues associated with deformations, and what do we understand about them, and how can we calculate them, and various kinds of deformations will be reviewed. And so it will be rather general presentation. Okay, so let me start from historical slide. That first evidence for non-spherical nuclear shape came from hyperfine interactions. So the very small splittings or changes of electronic transitions in atoms and molecules. And this is due to interaction of electrons with quadrupole moments of nuclei. So quadrupole moment of the nucleus generates a quadrupole field, and electrons, especially K shell electrons, interact with this quadrupole moment, and this gives rise to small shifts of energy levels of atoms. Okay, and so this was suggested in 1935 and 1936, and one of the actually people who suggested this, and this is actually a real effect which is very much used by experimentalists, was Henry Casimir, the same Casimir who is responsible for Casimir effect. It was his prize essay in Harlem. And then soon, around the same time, there were suggestions that perhaps atomic nuclei, which are non-spherical, can have rotational bands. So if nucleus is non-spherical, then it can rotate collectively. And if it can rotate collectively, it will emit characteristic gamma rays. And the observation of this gamma rays, usually E2 and E1 transitions, can be coupled to the presence of non-spherical shapes. So ideally spherical nucleus cannot rotate because you cannot define reorientation of this object in space. Okay, so the nuclear deformation is an example of the Yantellar effect. Yantellar effect was proposed, or Yantellar theorem was formulated in 1937 by Young and Teller in London. They collaborated on this, and this was pertaining to molecules. And the theorem states that any nonlinear molecule with a degenerate electronic ground state will undergo a geometrical distortion, which removes this degeneracy, okay? Because the distortion lowers the overall energy of the species. So what is important in the proof is the presence of degeneracies. So we have degenerate electronic terms, and they are degenerate because of some symmetry. In molecules, those are usually point group symmetries, discrete symmetries. And then the molecular ground state does not like to be degenerated, so the degeneracy is removed due to the coupling between electrons and molecular or ionic vibrations. So there is this term in the interaction is called vibronic coupling, which is responsible for the interactions of electrons with molecule, with the ions, okay? And this interaction in certain cases is so strong that it can give rise to a symmetry broken shape. So this is actually an example taken from this relatively recent Nature Communication paper in which they were interested in fullerene ion you see this object has many, many point group symmetries, and actually the ground state is degenerate, is actually there are three levels which have the same energy, and this ion undergoes Yantellar effect, and this beautiful spatial symmetry becomes spontaneously broken. Okay, you can see degeneracy between those levels is removed, and this is the essence of Yantellar effect. I will comment in a moment about how does it happen in atomic nuclei. But the lesson from this slide is that degeneracies are important, degeneracies are lifted, degeneracies are related to symmetries. So it's important to have states of high symmetry in order to get deformations which break this symmetry. Okay, so as I said, in molecular physics, deformations are results of Yantellar effect, okay? And there is this degenerate, you have this degenerate electronic excitations and collective vibrations of the molecule, and those are maximally coupled in certain cases, and system develops stable deformation. In atomic nuclei, this is called, this was discussed for the first time by Bohr and Mottelson in their papers from 1952-53. And let me translate this molecular formulation of Yantellar effect into nuclear structure language. Any nuclear configuration can develop a stable, can develop a stable symmetry breaking deformation, provided the coupling between degenerate single nucleonic excitations and collective nuclear modes is strong. So the way it was discussed by Bohr and Mottelson was in terms of, say, you have a spherical core, like a doubly magic nucleus, and you have valence protons and neutrons. This is symbolized in this figure, okay? And then there is an interaction, effective interaction between valence nucleons and the core, okay? Core can vibrate, can undergo vibrations, for instance, quadruple vibrations, like in this figure. And the term which will be responsible for the coupling or interaction of those valence particles with vibrations, you know, can be schematically described through the multiple force. So this is the multiple moment of a single nucleon, valence nucleon, and this is collective coordinate representing nuclear vibrations. And this coupling sometimes can be strong, and it can be so strong that those vibrations here, basically from vibrating system becomes statically deformed, okay? And so this was Bohr-Mottelson explanation of nuclear deformation, which then led to the Nobel Prize. But you can see immediately from this is that there are those protons and neutrons which are moving in orbits, represented by this term, and those orbits, of course, are quantum mechanical orbits. So nuclear deformations will be really governed by shell effects. Nuclear liquid drop model does not have deformed shape in its equilibrium. The stable, the ground state of the liquid drop model, which is a macroscopic model, is a sphere. So in order to get non-spherical shapes, you need quantum mechanics. Okay, so you can think of the development of nuclear deformation as a shape transition or phase transition, okay? Phase transition in a finite system. So for certain nuclei, the energy as a function of, for instance, shape deformation has a strong minimum at spherical shape, and doubly magic nuclei belong to this category. So we call those nuclei as spherical. They are really rigid with respect to the to deviations from the spherical shape. And there are also of course, the lowest collective modes of those nuclei will be vibrational states in the swell. And there are collective nuclei, deformed nuclei, which, for instance, you can imagine as ellipsoids, okay? And for those nuclei, the energy would correspond to the minimum of energy in the mean field picture would correspond to non-zero deformation. And the fact that nuclei are deformed in the intrinsic state, of course, results in the rotational bands in the laboratory system, because those nuclei can rotate in space. If you have a non-spherical object, it can rotate, and rotation is associated with collective bands, okay? And then between those two limits, you have very many nuclei, which we call transitional, which does not have very well deformed or developed deformations. I mean, those energies here are relatively soft. So there are many, many states having similar deformations, of different deformations which have similar energies. Here, you cannot really define nuclear shape. The whole concept of shape and intrinsic system can be questioned, okay? So the easiest thing is to think about those two limits, spherical and deformed. Physics becomes rather messy when we talk about transitional nuclei, okay? So you can, since atomic nuclei are quantal systems, of course, and there are finite state effects, of course, the transition from here to here is rather smooth, okay? This is the order parameter. This is deformation critical parameter. So there's a smooth transition from here to here, and this is pretty deformations are not very well developed concepts here. Okay, quantum fluctuations around the minimum are very important. And you see, if this potential is very soft, if the energy is very soft, the quantum fluctuations will be everything. Okay. So, but let us assume for the time being that the nucleus is very well deformed, okay? That in the intrinsic system of the nucleus, you can view it as a deformed object, for instance, ellipsoid. So as was shown in the previous talk, one thing you can do is to expand the nuclear surface in terms of deformation parameters, alpha, and alpha are those coefficients in the front of spherical harmonics. You can expand the surface, which you can, for instance, define in terms of, say, the density, which is more or less 50% of the value in the interior. So this is the radius expansion. And if nucleus is axial, those parameters alpha are called beta, so beta deformations. So this expression for radius enters sometimes simple models of nuclear physics in which we have deformed mean potential, like Wood-Saxon potential, which was mentioned in the previous talk. So this is just a parameterization of the deformed nuclear field. Of course, in the microscopic models, in the self-consistent models, such as ab initio models or density functional theory in particular, which is the model for nuclear deformations, okay, there's no reason to use this expression because we have just three-dimensional density distributions. So a better way, actually, of defining deformation parameters is to define through observables. So this observable Q lambda 0 is a multiple moment here. It does not have, the magnetic quantum number does not have to be 0, but for simplicity, I just put it 0 here. So those multiple moments can be measured, for instance, through electromagnetic transition probabilities. In this way, this quantity is unobservable, and then you can define deformation of the multipolarity lambda directly through the moment. So this is measured. This is the radius, which can be taken as 1.2 times (8⁻³ Fermi. Okay, and then you have one-to-one correspondence between deformation, which are called beta tilde, and an observable. Okay, and there is of course no those two quantities, this beta here from this radius expansion. Sorry, the PowerPoint sometimes changes the slides for me. So those deformations from the moments and those deformations from the shape expansion are not identical. So one has to be very careful, okay, how one defines those deformation in particular models. So
but
this
the question is how big typical difference between them, like a few percent?
It can be very big. I mean, you go to super deformations, and this will be extremely big. Okay.
Can I ask for clarification? Can you go back?
Okay.
So what you call beta lambda is what Giuliano called beta lambda W Wood-Saxon. And what you call beta tilde lambda is what Giuliano called beta lambda. Is that correct?
I presume so, yes.
Okay.
The answer is yes. This quantity beta lambda here is what is used, for instance, in macroscopic, microscopic approaches, which are based on the potential which explicitly depends on deformations through this radius expansion. Okay?
Thank you.
Okay, I also would like to make a comment here that most people assume that deformations are isoscalar. That is, that the proton distribution and neutron distributions deformed exactly in the same way. And this does not have to be the case. You might have proton and neutron liquids deformed in different way. But at least right now, I will assume that deformations are isoscalar, okay? So a quick discussion of the nomenclature. So we have, for lambda equal to 1, we are dealing with dipole deformations. There are 3 isoscalar dipole deformations, which with magnetic quantum number, I'm sorry. Oh, gee, I will probably stop using mouse. Mu -1, 0, and 1. But we have also 3 conditions to fix the center of mass of the intrinsic system. And we can fix those conditions, okay, using this equation. So in this way, we eliminate isoscalar dipole deformations. So there are no isoscalar dipole deformations if the center of the intrinsic system is at 0. But of course, there might be isovector dipole deformations. So those are not eliminated from this condition, and those isovector dipole deformations can be important in some cases, for instance, when we are dealing with strongly deformed octuple shapes. And then for quadruple deformations, there are 5 degrees of freedom, 5 magnetic quantum numbers, -2 up to 2, okay? And there are 3 of those deformations can be fixed by defining 3 intrinsic system by means of 3 Euler angular rotations. So this leaves only 2 deformations. There are 2 isoscalar quadruple deformations, alpha 2, 0 and alpha 2, 2. And they are usually parameterized through those parameters, deformation parameters, beta and gamma Bohr, Mottelson, Bohr deformation parameters, beta, which is beta 2, and gamma. Gamma stands for triaxiality. If gamma is equal to 0 degrees or 60 degrees, we are dealing with axial shapes. And there are other deformations, such as octuple deformations, lambda 3, lambda 4 hexadecapole deformations, lambda equal to 5, dotetracontrapole, or lambda 6, hexacontratetrapole. And they are all sometimes utilized, or they sometimes are predicted by calculations. I will actually show you some of those.
Sorry,
okay.
What's the color indicates? It's a different nuclear distribution.
I'm sorry.
Yeah.
So this is just a nice graphical representation of various shapes. So various shapes. So beta 0 spherical shape, beta 2 0 greater than 0 prolate shape, beta 2 0 less than 0 oblate shape. Hexadecapole deformation has this bulge here in the equator. Okay?
But the color doesn't mean any.
Looks like the color
nuclear
is
distribution.
Color is just to show better the shapes.
Okay, thank you.
So chromo technique here is used to illustrate the shapes. So there are very many precise ways to determine deformation experimentally, okay? So Catherine will be talking about various techniques. I just want to list some. The many powerful low energy methods exist to get information about intrinsic nuclear shapes. The most important are Coulomb excitation, in which one can actually extract deformations beta and gamma from the so-called quadruple invariance by measuring various multiple moments of transitions between low-lying levels. There are strongly interacting probes, like experiments in which we get information on deformations by scattering protons to alpha particles of nuclei, electron scattering, traditional way, lifetime measurements. We measure lifetimes of low energy nuclear transitions, and those lifetimes are related to reduced transition probabilities, and those can be related to those multiple moments. The structure of muonic atoms, a muon can enter nuclear interior, and if nuclear interior is deformed, the levels of muonic atoms will change. And there are electronic hyperfine techniques, which gives you directly quadruple moments. So this is this Casimir idea, right? And also charge radii depend on deformations. Those can also be extracted from atomic measurements. There are also collective modes in atomic nuclei, like giant vibrations of atomic nuclei, which will be impacted by nuclear shape deformations. Rotational bands, as I said, are impacted by the presence of internal deformation. So here on this slide, I have two examples of nuclear deformations. This one here is the intrinsic shape of deuteron. Okay, this is, so here the natural quantization axis is given by angular momentum of deuteron. The projection of angular momentum, one on the third axis, which can be 1 or 0, right? So in one of those projections, deuteron looks like this, and as you can see, it is certainly not spherical. This is actually a very beautiful experiment in which one could do electron scattering on stable samarium-152, and by means of measuring form factors for electronic, for transitions between various excited states of samarium, those radial multiple form factors can be then combined into deformed density distribution of samarium. Okay, just a very quick comment. I really don't want you to look at these equations, that in many experiments which deal with electromagnetic force. Okay, one is measuring charge density distribution. Charge density distribution, spherical or deformed, actually depends on many factors, not just proton distribution. This charge density depends on nuclear charge form factors, which depends, which depends on intrinsic proton and neutron electromagnetic form factors, because protons and neutrons themselves have density distribution. There's also magnetic contribution to this charge density, okay, coming from the fact that you have currents and magnetic moments, okay. So this is just a comment that in sophisticated nuclear structure calculations, one tries to take into account all those effects, also when talking about nuclear shapes. Okay, so another interesting example which tells us that the deformations reveal, you know, the phase in various experiments. On the right-hand side, you can see charge radii of mercury isotopes, and the blue experimental symbols correspond to the heavier mercury isotopes. You can see small staggering between those charge radii, which can be explained by pairing correlations on nuclear superfluidity. Those nuclei, those mercury isotopes here, are oblate deformed. They are weakly deformed, but oblate deformed. As you will go to neutron deficient mercury isotopes here, you can see that there's a dramatic staggering between charge radii, which can be explained actually through nuclear deformation, because we know that root mean square radius of deformed density distribution is larger than spherical, and in the leading order, this would be related to quadruple shape, okay? Those new mercury isotopes actually are very interesting because those are great examples of shape coexistence. So during a previous talk, there was an impression that the nucleus has one shape. Every state of the nucleus might have different shape, okay? The ground state might have different shapes than, you know, low-lying first excited state, which can be long-lived, okay? It's impossible to say that this nucleus has a shape. Various states will have different shapes. And as you can see, if you look at spectra of those mercury isotopes, the more neutron-rich ones really look like vibrators. Those are weakly deformed structures. But around here, and you see those levels marked in red color, okay, you see rotational bands. Those are well-deformed prolate shapes which show rotational bands. So in one nucleus, you have coexistence of spherical and deformed shapes. If you plot energy as a function of Jj plus 1, where J is angular momentum, this will look like this. There will be a crossing or coexistence of those weakly deformed, well-deformed configurations. So, as I told you earlier, the presence of a broken symmetry in the intrinsic system, for instance, quadruple deformation, quadruple shape breaks rotational invariance, right, internally, okay, manifests itself in the collective bands in the laboratory system. So uranium-238 here, okay, is very well deformed. It looks like this. It can rotate around the axis perpendicular to the symmetry axis. And in the laboratory system, it shows this kind of collective rotational band, very regular band. And all those states are connected through E2 transitions. And those E2 transitions are related to the quadruple moment of uranium. But if you go to radium-220, which is another deformed actinide nucleus, if you look at the spectrum in the laboratory system, so this is actually experimental spectrum, you see that it shows alternating parity band. That is, you have a one band which consists of levels which have negative parity and positive parity. And if you would show such a diagram to atomic experimentalists who deals with collective states of molecules, this person would tell you that this object in the intrinsic system must have parity broken. So indeed, radium-220 in the intrinsic system looks like a pair, is predicted to be a pear-shaped nucleus with octuple deformation. So the presence of two symmetries which are broken internally, that is parity and rotational invariance, gives rise to this band. So this is the problem which I have with zirconium-96, for instance, which is known to have triple shape coexistence, is itself very weakly deformed, that if there were strong octuple deformations of the order which were presented in the previous talk, I would love to see this kind of alternating parity structure in the laboratory system. And this is one more example. This is dysprosium-152, which shows basically three kinds of spectra in one nucleus. One, you have this collective band, which corresponds to moderate proline deformation. You have this structure here, which does not look collective at all and corresponds to non-collective, nearly spherical shapes. And you have this series of bands, several rotational bands, associated with super deformed rotation. So in this shape, this dysprosium-152 looks like a 2-to-1 ellipsoid. Okay, so this takes me to interesting topic of the laboratory frame and intrinsic frame. So we can talk about deformations once we define intrinsic frame, okay? So in some cases this can be done, but in many cases we have difficulties with it. So if the nucleus is very well deformed, like here, okay, and let us assume for simplicity that the nucleus is axial, then if this is nuclear shape, intrinsic nuclear shape, and this is angular momentum, then the projection of the angular momentum on the symmetry axis of the nucleus is a good quantum number. It's called K, okay? And then in this case, life is easy, and you can, for instance, relate the quadrupole moment of this ellipsoid of the nucleus, okay, to the quadrupole moment which you measure in the laboratory system. So there exists a transformation between intrinsic and laboratory system. And the coefficient here is related to Clebsch-Gordan coefficients corresponding to the transition from intrinsic to the laboratory. Okay, so this represents the relative motion of the intrinsic system with respect to laboratory system. So relative rotation, where I is angular momentum and K is this quantum number. So you can see right away that the ground state, in the ground state of even nucleus, for which angular momentum is 0, hence K is 0, this coefficient is 0. So what you will measure in the laboratory system is always 0. The quadrupole moment of the ground state of an even nucleus is always 0, regardless of how well this nucleus is deformed intrinsically, right? So this tells you that this transition from the intrinsic to laboratory is a serious business. And also, the meaning of deformation depends on whether you talk about intrinsic or external system. So how to define the intrinsic system? Well, it's theoretically it's not trivial. If the system has well-developed deformations, one can do it. For a system which is transitional, it's tough, and I will comment on this by the end of the talk. How to extract intrinsic deformations in the lab system models. So you have ab initio approach, in which angular momentum is completely preserved. So strong interactions and electromagnetic interactions, conserved rotational invariance, right? So there is no intrinsic system per se. So one has to, in a model-dependent way, introduce intrinsic system in order to talk about deformations. So I just would like to mention one way in which one can very elegantly define intrinsic state in approaches which preserve symmetry. So that is laboratory system approaches. One can actually do it. Oh, sorry. One can do it by using actually the two-body density distribution. So this quantity is called conditional probability distribution. Okay, this basically tells you what is the probability to find a nucleon fermion in state I if another fermion is in state Rj. So this quantity depends on two coordinates. So so R naught is the point of observation, and R basically runs all over the place. So this shows you a nice example from this Fisreff letter paper from 2006. So this corresponds to a system of bosons in a cylindrical trap. Okay, so you have several bosonic atoms, okay, which are in a cylindrical trap. So the system, in principle, trap has cylindrical symmetry, so is totally invariant with respect to rotations along the symmetry axis. But if you do calculations in the intrinsic system, you see those 1, 2, 3, 4, 5, 6, 7 atoms, right? 7 atoms which are distributed in this way. So this is the intrinsic system picture. But if you go to the laboratory system, because we know that angular momentum is conserved, this is what you will get. This is portion C. This is the distribution corresponding to angular momentum projected state. And of course, it should be like this because angular momentum is conserved. So there is no favored direction here. So JZ, third component, right, of angular momentum. But by looking at this quantity and taking as R naught here, this point, so we are effectively breaking, right, the symmetry. By defining this observation point, you can right away get this P quantity here, CPD, can show you the distribution of those bosons in the intrinsic state. So this could be one possible way, which has actually a lot to do with those two-body densities, which were presented in the previous talk. Okay. In a moment, I will show you examples of systematics of those deformations. Just would like to go back to Bohr and Mottelson, okay? If you go to Bohr Mottelson volume 2, nuclear structure, actually pretty good book for those of you who never studied nuclear structure, okay? You can see that there are many properties, for instance, of quadrupole deformations, which you can explain through the multiple, or quadrupole interactions. So if you take a schematic Hamiltonian, which is H naught, think of spherical Hamiltonian plus residual interaction, which is multiple, quadrupole interaction, which is built of isoscalar operators, Qn plus Qp, quadrupole moments of protons and neutrons, and isovector. So this is when protons and neutrons are deformed differently, okay? This kind of interaction can tell you a lot about actually nuclear deformations. And I advertise those two papers, the one on quadrupole deformations and one on octuple deformations. This Hamiltonian H can actually predict both low-lying quadrupole modes, low-lying quadrupole vibrations, but also giant resonances, those modes which correspond to giant vibrations of nuclear surface. Those modes are in the energy region of 12 to 15 megaelectronvolts. But those modes actually impact dramatically low energy collective or quadrupole states. So for instance, one can show in this schematic Hamiltonian that the quadrupole moment of the nucleus, Q lambda here, can be viewed in Bohr-Mendelssohn picture as the quadrupole moment of all those valence protons and neutrons, plus the part which corresponds to polarization of the core, the polarization due to presence of valence particles, okay? So the quadrupole moment is not just the quadrupole moment of valence particles, okay? The polarization effects are large, and that in the case of quadrupole vibrations, quadrupole deformations, the second term, polarization term, is of the order of the single particle term. So you see 50% of nuclear deformation comes from polarization, which comes from decoupling to giant quadrupole resonance, a mode which is at 15 megaelectronvolts. So this is actually a big problem for ab initio theory, you know, of, say, deformations, because usually those models are written in spherical Hilbert space. They cannot go to 2H bar omega excitations, which are characteristic of giant resonances. So those models usually dramatically underpredict quadrupole deformations. So I do not really have time to discuss it. The natural formalism for nuclear shapes and nuclear deformations is density functional theory, because the whole formalism is written in language of nucleonic densities, which can be spherical, which can be deformed. And we have two kinds of densities, proton densities, neutron densities, okay? You have interesting aspects of nuclear density functional theory. The nucleus is self-bound, superfluidity is important, okay? And the basic, the important input to energy density, nuclear density functional theory is energy density functional, which basically is the energy density of the nucleus written in terms of various nucleonic densities and currents. And very often those are local densities and currents, because life is much easier with local densities, but they can be non-local. And actually gamma of EDF contains non-local piece, Goni density, energy density functional. You will see many results of Goni calculations, and this program actually corresponds to non-local energy density functionals. Okay. The important aspect again is that the minimum energy in the nuclear DFT can correspond to the density which is deformed. So the ground state of the nucleus is automatically in this picture can correspond to broken symmetry. Okay. And deformations can be extracted from DFT densities exactly the same way we do it in experiment. We just calculate multiple moment of the density, and this is this beta tilde deformation, right? Okay, so what one can do, in principle, one can expand this microscopic DFT density into multiples, those quantities rho lambda. are related to density radial form factors, okay? And this can be related to those quantities which I showed earlier from the electron scattering experiments, those radial multiple wave functions. And if you look, for instance, into deformation energy of the nucleus, such as radium-224, which has both quadruple and deformed shapes, you can see that actually various multiples, 1, 2, 3, 4, 5, 6, etc., really contribute to the binding energy of the system. So it's not that there's only quadruple deformation or octuple deformation, various multiples contribute. Okay, so in this part of the talk, I will briefly review the systematics for various nuclear deformations. So what is the trend of deformations with shell filling? And I understand Anatoly will be talking a lot about those deformations computed in relativistic or covariant density functional theory. I don't know whether George is still here at the audience, but this physics letters here paper is his early paper in which he, for the first time, predicted the behavior of various deformations as a function of shell filling. So you have a magic nucleus and you add particles on the top of this magic nucleus. So you are slowly filling the valence shell. And in the model which was proposed by George, okay, where mu is the partial filling of the valence shell in the middle of the shell, this would be 1/2, right? So we see that quadruple moment has maximum. Nuclei in the middle of the shell usually have the largest deformation. Hexadecouple moment depends differently. At the beginning of the shell is large, and then goes through 0 and changes sign. If you think about Y6 moment, it will go like this, okay? It will have 2 zeros when you go through the shell. There's a nice paper by Yantellar from 1981 here, which parameterizes all those shapes. So let me show you some global predictions. So this shows predicted quadruple deformations in nuclei in the density functional theory calculations using various energy density functionals. Those are marked by those symbols UniDef1, SV mean, etc. The large deformations, the prolate deformations are red, the oblate deformations are blue, nuclei which are close to magic, that is those magic nuclei marked by dashed lines, okay, are usually spherical, that is white. You can see that the general pattern is exactly as in this old model by George. Okay, the nuclei in the middle of the shell between magic gaps are very well deformed. The oblate shapes happen on the transition between prolate shapes and spherical systems. But the pattern is extremely similar in all those models. And these are isovector quadruple deformations, okay? So these are the differences between proton and neutron quadruple moments as extracted from densities. And you can see that those isovector deformations are indeed very, very small. So if typical quadruple deformation is of the order of 0.2, I mean those differences between beta and P and, and beta neutron and proton deformations are 1 order of magnitude less. So in the zeroth order, you can assume that protons and neutrons are deformed in the same way.
So are there actually experimental evidence that protons and neutrons, when they are well deformed, are there measurements to show they could see something?
Well, it's very difficult to measure neutron distributions, okay? So everything can be, it's difficult to talk about experimental evidence. Of course, you can extract, you know, for instance, proton and neutron scattering lengths in the interactions involving strong probes, like protons and alphas, okay? But I don't believe that there's any compelling evidence, you know, for different proton and neutron density deformations.
So in most of this model, they actually predict, look like the neutrons have a smaller deformation than proton, right?
In which models?
They all show the blue, the color is always blue.
Oh yes, oh yes. But look, this is on the order of experimental error bars.
In the relativistic models, it's opposite sign
Oh,
in most of the cases.
Okay. So, and these are hexadecoupled deformations. As you remember from the simple picture, you know, was that as you go into the shell, you go beyond magic, doubly magic nucleus, you will first have positive hexadecoupled moments, and then you will get something close to zero, and then negative hexadecoupled moments. And calculations like these ones here, which are based on say macroscopic, microscopic model. So deformations are considered as degrees of freedom. So those this deformation beta 4 here is really beta 4 Wood-Saxon, okay? Using the language of the previous talk. So, but you see that this general pattern is really confirmed by theory. And here you have examples of hexadecoupled deformations as extracted from alpha prime and EE prime reactions for various rare earth nuclei, from neodymium up to osmium, okay? So in well-deformed nuclei, you have to do coupled channel analysis, and sometimes experimentally, you may have two different solutions. Like here, you have one set of solutions with hexadecoupled deformation greater than zero and some with less than zero. And this is because of interference effects. But this just shows you that there are, you know, there is some amount of experimental data on higher order multipolarities. And this is, since you really asked for this, so these are the ground state hexa contra tetrapole deformations in nuclei. And the pattern here is more complex. You have those two zeros, right, of the distribution. And again, the simple model seems to work.
So can I ask a question on the hexadecoupled, the landscape you showed 2 slides ago? So when you go to like you go to mid shell and then you go to over the mid shell, then the sign changes.
Yes.
That's where you also have the oblate deformation, right? So do you have a simple explanation how these two, the beta 2 and beta 4, the sign, how they are correlated? What's the reason for this kind of sort of like cancellation or whatever?
No, the presence of oblate shapes is why are some nuclei oblate?
No, I understand the oblate, but the beta 4 somehow the sign change of the beta 4 is correlated with the
So
sign.
beta 4, sign of beta 4 is a simple geometrical argument. As you are filling the shells above, you know, in a given shell, you will first go through the levels which have large intrinsic hexadecoupled moments. And then there will be levels which have negative hexadecoupled moments. And this will change, this will impact the total hexadecoupled moment of the system. So in those papers, in this paper, you have very simple geometry discussed. There is simple parametrization, which also talks about it, okay? So explanation is really simple. It's just geometry of a single J shell. Now, there was also discussion of triaxial shapes. It's very difficult to talk about triaxial nuclei because they're all very soft. But the best triaxial nuclei are actually the nuclei from this mass 100 region, like molybdenum 108 and molybdenum 106, okay? Those nuclei have triaxial deformations, you know, which are relatively deep, like several hundred kiloelectronvolts. But clearly, you know, since look at this energy scale, this is 500 keV, this is 1 MeV. So all this area here corresponds to very similar energy. So it's difficult to say what is the triaxial shape of this nucleus. Well, this corresponds to the minimum of energy, but all those shapes are more or less equivalent. So this is what is so difficult about the soft systems. Yet those are the best triaxial systems according to experimental evidence. And if you would like to read more, I give lots of references in this talk. Now we move to octuple deformations. I think that I still have like 5 minutes, right?
Yeah, yes.
Yes. So
you have a half hour.
Yeah. Yes. So there are some nuclei which are believed to be pear-shaped in the intrinsic system. Okay, and this is a shell effect for nuclei for which Fermi level is between two orbits which have different parity and change in angular momentum by 3. Okay, delta L, delta J equal to 3. There is an opportunity for strong octuple coupling, okay? So this diagram from this paper shows the systematics of octuple deformations. So the calculations were done with several energy density functionals, like nine energy density functionals, and various symbols indicate the model multiplicity. For instance, if all 9 models which were employed here predict nucleus to have octuple shape, so this is marked by a star, okay? So you see that there are very few nuclei in the whole landscape, especially when we talk about nuclei close to stability line, which are expected to be octupally deformed. Nuclei like barium-146, like radium-224, thorium-224, okay? So actinides and lanthanides here. So there are some good candidates, but not that many, okay? And they show many fingerprints of octuple shapes like those alternating parity bands or enhanced electric dipole transitions and whatnot. Okay, so here you have calculations of octuple and quadruple deformations in this nuclei, and there are also octuple energy. So this is the gain in energy which one expects due to the octuple degree of freedom. And you see that the difference between reflection symmetric and reflection asymmetric nucleus in the best cases is like 2 MeV if you assume a mean field picture without 0-point correlations. Okay, and this shows that for nuclei which are well deformed in terms of quadruple and octuple, there's a very good agreement between the moments, Q2 moments, left-hand side, and Q3 moments, right-hand side, okay, experiment and theory. And so things work very well. As I said earlier, those lambda equal to 5 couplings are very important in order to generate proper pear-shaped nuclei. Okay, and the last comment here before I finish is on the generator coordinate approach. Okay, so this diagram shows various energy surfaces or energy curves for sulfur isotopes. This was just convenient to take sulfurs because you have variety of shapes for different models. As you can see, you can have oblate shapes, negative beta 2, prolate shapes, positive beta 2, okay? But there are also models which predict extremely soft systems, okay? So depending on the model, depending on the shell structure, predicted by a given model, you might really have very different shapes. And in some models, shapes are totally flat. Look, for instance, in this model, this nucleus sulfur-38 has surface here, which is more or less, which has constant energy. So what is the shape for this nucleus? Okay, well, in order to treat such systems, one has to go beyond the concept of a single shape. One has to basically mix in calculations a number of shapes. And this is the concept of multi-reference approach. And this will be discussed by Bali and Rodriguez in their talks, I presume, because they will talk about GCM. And this is something which is very well known in atomic molecules when you have a wave function, which depends on slow coordinates, ionic coordinates, and fast electron coordinates, and you build wave function in this way. So for each position of slow coordinates, one solves the eigen problem, okay, for each position of slow ionic coordinates, one can solve electronic problem. And then the total wave function can be written in this way, where ionic wave functions, nuclear wave functions, and electronic wave functions are coupled strongly. Okay, so this is very similar to what we do in generator coordinate method. We carry out calculations using DFT for different values of deformation, like quadruple moment, octuple moment, right? So we have those HFB wave functions, DFT wave functions, and then we assume that the total wave function in the will be superposition of those, and eventually we integrate over those collective coordinates. So the quadruple moment or octuple moment does not appear on the left-hand side because it has been integrated out, okay? So if the situation is like in those soft sulfur isotopes, right, the wave function will be really a superposition of wave functions corresponding to various shapes. That's it, okay? And of course, here the choice of this collective coordinate Q is ours. If we have a good intuition, you know, we can improve the physics description. If you know that in a given region, quadruple and octuple degrees of freedom are important, then for Q, you'll take quadruple moments and octuple moments. But the more sophisticated this generator coordinate method is, the more collective coordinates one takes into account. Okay, so these are actually calculations which involve Madrid group, right? So this is example of GCM calculations for barium-144. Barium-144 is the nucleus which is expected to have those octuple effects, okay? You see here in this diagram, on the level of mean field, pure one single reference DFT, the potential energy as a function of beta 2 and beta 3, and those are beta 2 and beta 3 tilde. You know, the deformations do not enter formalism per se explicitly. So you see that the surface is extremely soft here in this direction. Okay, the nucleus can really take any value of beta 3, you know, in this range. And so one has to take wave functions, a combination of all those deformations, and those are the collective wave functions. As you can see, that the ground state wave function of barium-144 is really a democratic combination of contributions coming from all those points here. So no single shape, guys, here. And so this exercise you can play for various states of positive and negative parity. And those collective wave functions actually can be now related to experiment. And this is shown. This is very beautiful work by Thomas Rodriguez, in which he analyzed a nucleus, cadmium-112, which in fact has several coexisting shapes. You see experimentally, there are several 0+ states, those 0 plus states will correspond to different distribution of quadruple deformations. But this kind of calculations involving also angular momentum projection are able to calculate really great details of what experimentalists see. I would say that the diagram shown in the left-hand side has strong relevance qualitatively, quantitatively to what is seen on the right-hand side, okay? And in this way, you can find the correspondence between deformations and what is seen in the laboratory system, okay? So nuclear theory is moving to such calculations, which do not involve schematic labels, but rather microscopic picture. So summary of the talk. So let me wrap it up. So majority of nuclei are deformed due to the Yantellar effect, right? So only nuclei which are close to magic numbers are really honest to goodness spherical, okay, in the ground state. Nuclear deformations are not fundamental degrees of freedom. These are just useful quantities which we can use to characterize nucleonic densities. And nucleonic densities can be probed experimentally, okay, through various techniques. Nuclear deformations, both the appearance and the magnitude are governed by microscopic shell effects. So nuclear deformations are due to the fact that protons and neutrons move in shells, okay? But oftentimes, this motion is very correlated, hence this systematics of those deformations is very regular. The presence of intrinsic deformed shapes results in occurrence of collective excitations in the laboratory system. So if the nucleus is deformed in certain way, this deformation will result in collective levels in the laboratory system. Think of my example of radium-226 or 224 and this alternating parity rotational band. So if an experimentalist shows me spectrum, nuclear spectrum, I can just look at this and I can make a speculation, which is very reasonable, whether this nucleus has quadruple deformation, octuple deformation, or whatnot. So deformations are configuration dependent. Every nuclear state, in principle, has different deformation. And sometimes nucleus state may have very many nuclear deformations if this nucleus is soft. Okay, so this is the last point. This is really a warning here, that in many cases, nuclear deformation cannot be defined as intrinsic configurations having similar shape, as intrinsic configurations having similar shapes appear close in energy. In such cases, multi-reference analysis, such as GCM, is needed, okay? So the question is, to what extent in your relativistic heavier, in which your extremely high energy collisions, you will probe those individual components of the GCM wave functions. I presume that this is what you will actually do. So that's basically it. This is an overview of nuclear deformations.
Okay, thank you. By the way, can you, Giuliano and Rita, can you have you sent your slides to the secretary? If you can send it, so we will. Then it's good for us to discuss in the afternoon. We need to lot of interesting idea, but we.
I will send it as a PDF file. Okay.
Yeah, you can send to us also. It's fine, or send to the secretary.
Okay, will do.
Yeah, thank you. So questions? Yeah, Uli.
Yeah, a question about this generic case of softness, where you have to really talk about multiple possibilities for the deformation. My question is, can this be described probabilistically? Can you think of that as a probability distribution of deformation parameters, or is it more quantum mechanical and you have to talk about?
Yeah, so this is exactly what is shown here, Uli. Okay, so the collective wave functions, which you calculate, in the generator coding method, can be really viewed as probabilities that nucleus is in a given shape, right?
So that's good news, I think.
Yeah, this is why I said that this is perhaps what you see experimentally.
Although it's not fully a probability distribution because the GCM works on a non-orthogonal basis, so it's not really a probability, but it's the closest we are in a sense. So
yeah, so there's a subtle distinction between two kinds of collective wave functions. So there's this function, the function f, which defines GCM wave function, and there's a probability distribution, and this is not the same. But for this meeting, I think it does not make any sense now to explain the difference.
Yeah, I agree. I guess.
Let us not get too technical. I was trying to make this talk as least technical as possible.
Sure. But you could calculate the two-point correlation function, right? In principle, then
yes.
We can then make a more direct connection.
Like you mean like the
two body. Yeah.
But it's very time consuming. It's possible, but it's very time consuming.
What I was trying to say in my talk that this is the best way from those two-body correlation functions, or the two-body distributions, right? To get information about intrinsic states. That's the best way.
More questions? I don't see any people on the Zoom. Please raise your hand so we can see. But more questions in the room. Now, so I have a question. Just maybe saying something stupid, but in the nuclear structure, in order to know the shape of the ground state, you need to measure the excitation spectra, right? And you also mentioned that when you have excitations, the intrinsic deformation of the excited state can be different from ground state. So to me, that in order to know something about ground state, you need to know how the shape changes, evolves as you excite it. So, but in Hermitian collation, if we only probe the ground state, in principle, we don't need to know the evolution. Of course, that's a loss of information, but it's also a little bit blessing, right? Because we only need to know the shape of the ground state, but it may still fluctuate, but at least it may avoid, it's okay. The question whether you have such a possibility that the ground state still have some kind of soft, but it's sort of static deformation. And then you have the excited state actually is not very low lying. So if you have excited state, then the deformation changes. Therefore, your odd even staggering, for example, is you don't see the expected pattern, but that doesn't mean your ground state does not have a static shape. I may formulate this is wrong, but I'm saying
no, I understand what you say. I think
in the ground state where you go to excited states and the shape is changed, so you do not see this odd even staggering.
Yes, so of course excited states might have different deformations. So I think that in order to probe this in a proper systematic way, I would like to see your experiments done on nuclei for which are fairly rigid, for which nuclear structure experiment and nuclear structure theory can say those nuclei have more or less well-defined shape around the ground state, okay? And this will eliminate many confusions. Moreover, if your analysis is done correctly, then those deformations from your analysis should be very close to what one measures in other nuclear experiments.
Yes.
So to go to crazy nuclei like zirconium-96, which is multiple shape coexistence, which has many low-lying collective states which admix to the ground state, makes little sense to me. I know that this is what you do because you got this data, but I think as a nuclear structure person, okay, I would love to see some solid benchmarking here.
Yeah. Well, very good point. I think we would love to do that benchmark. We also to convince ourselves we are doing something. Like for example,
It's not only that you want.
208 and uranium 238, right?
Yeah.
That will be something that is
That would be good. Uranium is fairly rigid. It's not that you want to convince yourself, you also want to convince nuclear structure community, right?
yes,
That what you do is very sound.
yes.
Carlos,
You know, the problem which I see that maybe I'm wrong, your coupling to people who deal with collective states in nuclear experiment is not very strong. So you talk to nuclear theorists who do not really deal with experimental data. So I think that benchmarking should be done. Carlos, you want to say something?
Sorry. Wojtek, during your talk, you mentioned that GCM calculations were not really fully justified in the case of nuclear due to the because they assume slow motion. Is this quantified in a reasonable way?
Yes. So this is a very good point. You can always, but I view, Carlos, GCM as a variational approach. I can always take a wave function, which is superposition of states with various deformations. Okay, and then I just minimize the energy of the system.
This is always valid, right?
This is always valid, right?
Right.
So, of course, you can think about it in the same way, in Bohr-Oppenheimer way. You can even analyze those results in Bohr-Oppenheimer way, but you do not have to do it.
So, Wojtek, I have one more question. You have worked with the mean field calculations, in particular, Hartree-Fock-Bogoliubov and all the tweaks that one has to do with. We have worked for so many decades. So at this point of your career, what do you think are, the major problems, for example, for this case of deformation that mean field calculations still have to be improved? What do you think is left to do?
I think that well, there are many things. I do not believe, Carlos, that question of nuclear shape is a question for nuclear theory.
Okay.
We know why, and we know how. Okay, we know how they develop, and so at this point there are no big secrets really. Okay, but we still have sometimes difficulties understanding, say, coexistence effects.
Okay.
But the main issue in my mind is that Bali and Rodriguez and perhaps Robledo will tell you more about GCM, all this mixing of states. Okay, this is what we do on the top of standard single reference DFT. Okay. But I am asking myself, can we develop energy density functional, which will be complex, which will have, unusual density dependencies, which will give you a DFT answer, which will include all those correlations, which you have to put by hand by doing GCM. If I take original formulation of density functional theory, right, a la Consam, Honenberg, right? We know that in principle, we should be able, given, true functional, get everything which pertains to the ground state.
Okay.
So my question is, can one develop such functionals that all these multi-reference things, won't be really needed?
Yeah, you are the best person to answer the question.
Oh, my students and postdocs.
Okay. Okay, thank you.
Thank you.
Benjamin, you were saying something
I
about
was just going to
GCM.
say for the uranium, like we have already started, like for lead calculation and uranium, it's not even.
But if the GCM, this mixed state are not really orthogonal to each other, you did estimate the probability, right? In some way.
You do an estimation.
But is this a reliable or is this some?
I think the best we have, so it's
Okay.
the closest we have.
Right.
And as Vitek said,
Yeah.
what should be used, like, in my opinion.
Okay.
The first thing we can use is that if it doesn't work, maybe you can think about something else.
But that can be also a problem related to energy density function.
Yeah.
Because what they are getting in the calculation depends on, in reality, on the underlying single particle structure, because it creates this potential energy surfaces,
Right.
and different functions like Vitek show different initial potential energy surfaces. And when you start to mix them, like in GCM,
Yeah.
you will get different answers if you use different functions.
I mean, for the lead or uranium probably doesn't matter, right? But if you want to really understand the basic zirconium.
Yeah, soft
I mean,
systems
then this
Actually,
is
even
maybe.
even for uranium, I did
Okay.
calculation with Giuliano with a certain functional, and just, I could see like the functional like something like too deformed,
Okay.
and it will not give a good results. So even for large system,
Does it work for lead 208?
yeah.
Do you have a
lead-
model
lead
dependence
is
there?
easier because it's
It doesn't have-
spherical,
Mhm.
so the functional anyway is fitted to reproduce lead, so you will obtain always something that is spherical, but also could add that even after when you do the GCM, you will slightly deform your system.
Sure.
Even for, let's wait, the potential energy stress to be slightly deformed, so something like, I don't know, 0.05 in terms of beta, and you have to mix that. But the spherical approximation is good.
So once it's strongly deformed, even the GCM doesn't
It's
always
not
produce the
really the
same.
GCM, it's like, as André said, it's related to the function. If the function gives you
Function.
something that is wrong,
Okay.
you
I
can
see.
project, mix whatever you want, but if the energy surface
Yeah.
is stupid in the first place.
Okay. Okay, so we still have some time. If you guys want to come up with some questions, please.
Yeah, I will try to come at 5 p.m. of my time.
Okay, so I have a question since other people don't ask. So when you talk about Yantellar effect in the molecular,
Yes.
it's a coupling between electronic state and vibrational state. But the feature that then we discuss in the nuclear structure physics is they also have rotational states coming in, right? I just want to
Rotational states are manifestation of deformations. So the coupling is about vibrations, surface vibrations, okay, and nucleonic states.
Right.
So, I think that you can explain it all using, the Mexican hot potential of the Higgs mechanism, right? So this is really the spontaneous symmetry breaking. So you have the top point, right, in the Mexican hot potential, maximum of energy, right? And this corresponds to the spherical solution or completely symmetric solution. Then symmetry is broken internally. So we go down, okay, and we have potential in this direction. And this is the Higgs mode. And this is quadruple vibrations around the minimum. But we also have this Goldstone boson, which goes around. And this is related to the fact that you can rotate deformed systems, without any resistance. It costs you zero energy, right?
Yeah. But the impression I have is that because in the nuclear system, the effect, the coupling is much stronger than the molecular system, right? In terms of deformation and also.
Yes. So the good answer to this question is in molecular system, except for the crossing points, when configurations cross. Bohr-Oppenheimer works like a charm because the time scale for the nuclear motion is for the motion of ions, right, is very different from the motion of electrons. Electrons are extremely fast.
Yeah.
So separation is good. But look at the nucleus. The single particle time scale of the nucleus is 3 times 10 to the minus 23 seconds. So this is typical
rotation.
momentum around the Fermi level. And typical nuclear rotations and vibrations happen in the time scale, which is said order of magnitude slower, order of magnitude, but not many orders of magnitude. So this separation is extremely imperfect. But it still explains the phenomenon.
Right. Okay, that's very good. Yes, thank you.